this mass right here is the mass of the object. Mass of the object. Well, guess what? The mass of the object doesn't matter, once again. It's the same speed for any object that you put into space. This R right here cancels one of the R's right there. So what you're left with is capital G, constant, the mass of the planet, the constant, divided by the size of the circle, equals the velocity of the orbit. And that's velocity squared, so I take the square root of both sides. So if I have something just skim the Earth, that is, not have a big distance off the surface, but just skim the surface where it's basically just having a distance from the center of the Earth as like the radius of the planet, I bet if I put the radius of the planet here, of Earth, put the mass of Earth in, put G in, did this arithmetic, take a square root, this is going to be 8,000 meters per second. Exactly what we saw last week. Suddenly Newton knows how fast something has to go to stay in orbit. This is not going to be a mystery to him at all. He just doesn't have that number, but he still knows that this law is probably telling you the right thing. Right? He's not stupid. So he doesn't have to have that value for G to know that this thing is working and so forth. How does he know that this thing is working? He waits for about 20 years for the guys at the Royal Observatory to look at something. To them it's kind of boring, looking at the moon. But he needs to know precisely the period of the moon. We go on and the moon phases come back every like 29 days. I don't talk about the period. It's how does it align with the faraway stars behind it and so forth. And that's a number that's never been measured until they do that at the Royal Observatory, because you don't want the moon to align with the sun, you want it to align with the faraway stars. One is called a synodic rate, the other is a sidereal rate, and there's reasons why one is much better. You're trying to align with faraway objects that aren't moving, but the sun and the earth are moving around actually each other, so they actually make a wobble and so forth. So the close object is no good. And so he calculates with the law of gravitation, if the moon falls from that straight line 1/20th of an inch every second. So there's a calculation, but then he needs the actual data. And so when you actually look at the data of what the period of the sun happens to be, then you just use kinematics and you can see exactly how far it falls every second. And bang, right there it is. You can get exactly the result that you're looking for. So Newton's law of gravity is working pretty good. And then suddenly, and I'll finish this story on Wednesday, there's a planet that you can't see with your eye, just beyond, not just beyond, but it's beyond Saturn, the next one in line. And that's the planet Uranus. And you watch Uranus for a while, and you start measuring some distances and so forth, and suddenly it does not have the predicted path that Newton's law of gravity gives you. So this is a problem. And so you've got a choice. Well, the law is wrong. They only work sometimes or something. Or something else is going on. But when you actually look at Uranus, it's off at regular intervals, which tells you something probably interesting is taking place. And so if you actually right, I mean, a physicist in the 1800s says, all right, you might go ahead, so the law is probably telling you the right thing, but there's something else tugging on Uranus every so often. There's something beyond it. And so you do the calculation, right behind us, capital G, M1, M2 divided by R squared. You say, well, it has this mass, put this force on it to get Uranus out of the right or the wrong place, or whichever way you're looking at it. And it has to be this distance away from it. Look right here. Within 2 minutes, they discover Neptune. Neptune is discovered with Newton's law of gravity. It takes less than 2 minutes to find it. You can't see it with your eye. You have to put a telescope up there. So this is going to discover one of our planets in our solar system. This is great news for something like Newton's law of gravity, right? Because there's not a lot of corresponding data points that can say that it's going to work. Like we've got a few planets to play with and so forth. So the big discovery of the planet is probably good enough for us. But